Hi, I'm Peter Martinson. With me is Ben Dennison. We're with the LaRouche Political Action Committee, and we're going to give a short presentation which expands on some of the material that Lyndon LaRouche has already presented at the keynote of this conference.
From this vision you're presenting, Peter, I think we can now focus on the path we can take to get there, to achieve that. As Mr. LaRouche stated very clearly in his opening remarks in his keynote address, we have this current, multifaceted crisis in the world. And he made very clear we're at a point where we can no longer afford to have the types of conflict and warfare among nations, because we're at the point where that could lead to the self-extinction of the human species. And the alternative is exactly what you laid out and what's being discussed at this conference, which is a new vision for what mankind has to be. And as an integral part of that, as a beginning step for mankind taking that path into a new level of taking on these challenges, becoming a truly spacefaring species, we have this immediate threat of asteroids and comets. And so we're at a point where what the international declaration needs to be no warfare among nations. We need warfare against comets and asteroids. Those are threats that mankind needs to come to deal with. And the only way we can do that is by these types of programs we're talking about here. So I want to just give somewhat of a sketch of what this challenge is, a challenge being placed before our generation and the coming generations to conquer, to actually secure the existence of mankind on this planet, secure the defense of this planet from these threats that we know will happen at some point in the future. We know at some point there's going to be another asteroid impact. We know at some point, maybe distant in the future, there's going to be some comet impact again. So the question is, will the nations of the world come together now to take the necessary precautions to ensure that we can increase mankind's physical economic power to deal with these threats? And so we in the United States have been very interested in some of the discussion to make this the focus of international collaboration. For example, you had a reference in the winter of 2011 from Dmitry Rogozin, who was then proposing to the United States that the United States and Russia should collaborate on missile defense systems, but also defending the entire planet from the threat of asteroid impacts. And we in the United States think that is exactly the right type of approach to international collaboration. We should be collaborating with Russia, but also China and India, and forming a new bloc of nations focused on the defense and advance and physical economic advance of mankind first and foremost. And there's a number of somewhat similar proposals, such as the proposal for the IGMOS system, a system of international collaboration and sharing satellite data, beginning to develop forecasting capabilities, forecasting earthquakes, forecasting volcanoes before they occur, monitoring the entire Earth to give mankind disaster response capabilities and forecasting capabilities, and including looking for asteroids and comets. So these are the types of programs that the powerful nations of the world right now should be focusing and collaborating upon. Because if you just look at the threat, if you look at the asteroid threat, for example, so I'm going to talk about, you have two classes of threats we should be focused on. First, you have the question of asteroids, and then we'll get to the question of comets, which is a qualitatively different threat. But if you just take even just the simple issue of asteroids, we're essentially right now flying blind through our own solar system. Even just the inner region of the solar system, say between the orbit of Mars and the orbit of Venus, you have a huge population of asteroids. Now, most people think of asteroids in the main belt between Mars and Jupiter, and the vast majority are there. The vast majority of the asteroids are in that region, the so-called main belt of asteroids. But you also have a very significant population of near-Earth objects, near-Earth asteroids as they're called, which orbit anywhere between, they can come closer to the Sun than Venus even, they can go farther out than Mars, but they have characteristics where they tend to, a large number of these tend to cross the Earth's orbit on a regular basis. So these are the bodies that we should be immediately concerned about, because if they're crossing the Earth's orbit, if the Earth happens to be there at that point when they cross the Earth's orbit, then you get an impact. And these impacts are actually much more frequent than most people would tend to consider. I mean, you have a whole range of sizes of these objects. Some are very large, a lot of them are smaller. And even these smaller ones, we know can cause major damage. You know, probably the most famous example is the Tunguska impact in 1908 in Siberia. You know, and this is a relatively small object, relatively small asteroid or comet fragment, maybe about 30 to 50 meters across, so not a huge object. But when it came into the atmosphere, it comes in at such a high speed that it literally, you know, it's going from thousands and thousands of kilometers per second, smashing into the Earth's atmosphere, generating so much heat and slowing down so quickly that it literally explodes in the atmosphere. And what we think happened in 1908 was that this created a blast wave that came down over Siberia and then leveled an area of about 2,000 square kilometers of trees. Now, if you compare that size area, 2,000 square kilometers, with any major city in the United States, New York, Washington, D.C., San Francisco, you compare that with Moscow, you compare that with London, this would level any major city if it happened to hit over a major city. Now, the impacts of this size are relatively frequent, every few hundred years, we think. And but the problem is that we don't even know where most of these things are. If we can observe these and track their orbits, we can forecast years and decades into the future when they might intersect the Earth's orbit. You know, if we know the orbital parameters of an asteroid, granted there are some uncertainties, and some of these uncertainties can become subjects of new scientific breakthroughs potentially in investigating them. But the only way to get to that point is to begin to map out the inner solar system. And based on current estimates from NASA and other organizations, we have discovered maybe around 8 or 9,000 of these near-Earth objects, near-Earth asteroids. And we have then their orbits mapped out. We forecast their orbits decades into the future, and we can then see if we think that it might impact next year or in 20 years or in 50 years. Now, 7,000 to 8,000 might sound like a lot, but the current estimates are that the total population of objects down to about the size of a Tunguska-sized object up to the largest objects is somewhere in the range of 500,000. So we have discovered about 8,000 maybe of a population of 500,000. So it's a little over 1%. So we're right now essentially flying blind through the inner solar system. And this is not even, this first issue is not even a huge technological challenge to deal with. We could be putting infrared telescopes in orbit around the Earth, in orbit around Mars, or around Venus actually, either maybe in an orbit around the Sun similar to Venus's orbit. We could be putting these telescopes at the Earth-Sun Lagrange points, and we could begin to map this entire region. And so we can map this entire region and get a sense of this population. And that needs to be done. There's been a lot of discussion about proposals for how to do that. And that initiative needs to be taken up, like Peter mentioned, populating the solar system with these satellite systems to get the kind of readings we need of these bodies. Now that's one first step. We should also be looking at the question of comets, and I'll just treat this very quickly because this is a qualitatively different and more challenging threat, because these comets come from the farthest outer reaches of the solar system. Now, just to illustrate one example, in 1996, an amateur astronomer in Japan discovered a comet. When he discovered it, it was sometime in late January in 96. When he discovered it, it was just past the orbit of Mars, coming into the inner solar system. Now, in 2 months, since it was first discovered, we had no idea it was out there before then, had no clue it was coming into the inner solar system. And then we discovered it in late January. 2 months later, it passes by the Earth at 0.1 astronomical units. Now, in solar system terms, that's a close pass. There's been closer passes. You know, it's still a good amount of distance. But in terms of the solar system and the scales you're dealing with, that's a close pass. Now, this comet was about 4 kilometers across. If that would have hit the Earth, it would have had completely devastated the entire planet. That is a global effect. That's not just a small regional effect. This is not something that's 30 meters or 50 meters across, you know, creating an effect on a certain limited area. Once you get to the scale of 1 kilometer, 2 kilometers, 4 kilometers across, You're talking about global catastrophic effects. Now, this did miss with a good amount of distance, but the point to make is that we only had 2 months of warning time. Because these objects come from the far depths of the solar system and then come in to the inner solar system, with our current observation systems, we have little to no warning about when these things are coming. So this defines, so even though the comets are less frequent, this still defines an existential threat for the planet Earth and the solar system. And it defines some very interesting frontiers I just want to touch on, because if you take this particular comet, this one in 96, when we extrapolated what we think its orbit is to its full orbit to see when it goes back out into the outer reaches of the solar system, we think it actually travels out somewhere about 70 times the distance of Pluto. So we think Pluto is far away. This comet will go 70 times farther than that. It'll take it thousands of years to do so, but it'll go 70 times farther than we are from Pluto out into the outer reaches of the solar system. Now this is a completely unknown frontier area that we need to begin to think about, because the current theories are that this region is populated with trillions of cometary bodies. The current theories are that this so-called Oort cloud is a huge population of cometary fragments, comets and large bodies that orbit the entire solar system in these vast distances. And what we think is that as our whole solar system traverses through the galaxy, moves by other stars, moves through the spiral arms of our galaxy, moves up and down above and below the galactic plane, as our whole solar system, as we have evidence from various sources, is moving through our galactic system, this whole body of cometary, this whole region of cometary bodies becomes perturbed and affected by these galactic forces. And it is thought that these can then perturb these bodies and then send them into the inner regions of the solar system. So the point is, this is not a question we're going to solve in 10 years. But these are the considerations that, as we know, have caused the extinctions of thousands of species in the past. There's clear correlations that indicate that as our solar system is traveling through the galaxy, you have periodic cycles of mass extinctions and then mass growth, mass expansions of new species, and the creations of entire new types of life on the planet. So if you take this long-term view of the interaction of the solar system and the galaxy, you're defining an entire new frontier that mankind needs to begin to understand and investigate. And now, again, this is not a thing that's going to be solved in 10 years or 5 years or something, but this is a generational, multi-generational perspective that we should be looking towards. And so these are the issues that nations should be focused on. You know, and Mr. LaRouche's idea is that the United States, Russia, China, India need to come together, form a new economic bloc, form a credit system to facilitate the types of economic growth that will improve conditions on Earth and expand mankind's capabilities into space. And as Peter mentioned, probably the pinnacle, the forefront mission in this should be the Mars mission. We need to take the question of asteroid defense, comet defense, and take it from this physical economic perspective. How do we increase mankind's power to defend the planet and improve the conditions of life? That becomes a science driver program. And the best science driver program we have right now that can be a generational, 1 or 2 generation program is the development of the defense of Earth, but doing that by developing the whole nuclear and thermonuclear capability of mankind, including thermonuclear propulsion systems, to ensure mankind's safe travel from the moon to Mars, which will also give us vast new capabilities for defending the Earth from these asteroids and comets. It will give us vast new capabilities of going out to intercept these bodies if we do need to intercept them. But this all becomes subsumed by one conception of mankind moving out into space, moving into a thermonuclear platform for the entire economy, a thermonuclear-based mode of action for all of mankind. And today, getting the international agreements to commit to that mission for a generation or 2 generations. And the Mars mission should be a focus for that. So that is what we'd like to bring to the conference today. And we hope you enjoy your conference, and we'll talk to you again.